Hello students, welcome to lecture 31 of the online course on Nanophotonics, Plasmonics and Metamaterials. Today's lecture will be on transformation optics and invisibility cloaks. So here is the lecture outline. So transformation optics will discuss about the basis of it, the fundamentals, and what are the principles and mathematical forms in this particular field of science. And then we will take up some example of transformational optics and we will see how this helps us achieve some feature which are not naturally seen. Okay, something like you can actually make materials that give you refraction without reflection, and then you can also think of refraction at normal incidence, which is something not naturally occurring in the materials that we deal in day-to-day life. Okay, you can also think about cylindrical focusing from a planar interface. Okay, so we'll look into all of this and then finally we'll discuss about invisibility cloaks. So let's introduce transformation optics to you. So the first thing that should come to your mind is that this is coming from some sort of coordinate transformation. Okay, so the requirement for transformation optics comes from the fact that you want to bend light in a particular way depending on your will. So you may argue that there are graded index optics which allows you to do the same thing. So yes, so graded index optics can be considered that determines how light can propagate in a medium with particular dielectric and magnetic properties. Now when you take it further, you will be able to make light to do anything. Okay, so we'll look into those examples today. So let us first start with graded index material and see what happens there. In graded index materials, or GRIN, graded index green, okay, they allow optical rays to follow some curved trajectories which are basically governed by the profile of the refractive index Ny, and that is considered to be constant along x and z, but it only varies along y. So you can think of something like this. So here the refractive index basically varies only along the y direction. So in this case there is a gradient along the y direction, and as you can see, a ray can get bent from this interface at a different angle. So the incoming angle was theta, which was function of the position y, but then it changes. Okay, so this happens because this bending basically happens because the refractive index along y is also changing. So you can say that at a height of y it was Ny, okay, and at a different height, okay, here the refractive index changes to Ny plus the slope of this refractive index profile. So that is dN over dy, and then how much you have changed along y, that is delta y. So this gives you the new refractive index at this particular point. So this graded index materials allow you to direct light, and you can actually make light to take any bent path. Now for isotropic materials with graded electric permittivity epsilon r and magnetic permeability mu r, Maxwell's equation will give rise to generalized Helmholtz equations which were solved for layered and periodic structures such as photonic crystals. We have seen this already before. Now the synthesis problem of these graded index materials is more challenging than the analysis problem in two respects. First, they will require much advanced mathematical tools. As you can understand, the refractive index continuously varies along one direction or the other, and also the physical implementation of this kind of graded medium will require the use of metamaterials constructed from the components that are available or which are basically configured in a particular spatial arrangement, okay, and they should be supported by the current fabrication technology. So these are the kind of requirements, or you can say limitations, getting imposed onto the graded index materials because of the current technology status. So both mathematical, you require advanced mathematical tools, so the analytical study is difficult, as well as the fabrication of graded index materials will be challenging as well. Now to overcome these limitations, you can think of transformational optics. Now transformational optics acts as a mathematical tool that facilitates the design of optical materials which can guide light along any desired trajectory. So you are able to achieve the similar functionality of the graded index optics, but here also you can do a lot of new stuff, okay, not lot of new cool stuff, I should say. The underlying concept here lies on a geometrical transformation that converts simple trajectories into desired ones, okay. So in order that Maxwell's equation will remain valid, and the optical parameters associated with the transformed equivalent system must also be modified, and this establishes the character of the required optical material. So you require new kind of material to do this trick for you, okay. So as a simple example of such equivalence, you can think of a local compression of the coordinate system by a scaling factor which is equivalent to the local increase in the refractive index by the same factor, okay. So it is like if you compress one coordinate system by a scaling factor, okay, in one case you can, in another case you increase the local refractive index by the same factor, what will happen? The optical path length in both the cases will be similar, okay. And how optical path length is defined? It is the physical length multiplied by the refractive index, okay. So in one case the physical length is coming down, refractive index is remaining same. In other case the physical length remains same, but the refractive index is scaling up, so their product remains same, okay. So that is the optical path length. So a local compression of the coordinate system. So if you are compressing any material along z direction by a factor of a, that can be also assumed to have similar effect as if you have the same dimensions along z, but the material now have a refractive index n a. N was the previous refractive index, now it will have Na refractive index, okay. Now transformational optics, let us see how you do the design. So there is a 3-step design procedure which will provide the guidance. So you first begin with a pilot physical system for which the optical trajectories are known, such as a homogeneous and isotropic material, and then you find a coordinate transformation that convert these trajectories to the desired ones, okay. And then you determine the transformed physical parameters of the equivalent material. So this is the third step, and with this new material you will be able to obtain the desired optical trajectories in the original coordinate system. So this is what you are looking for, okay. So you want the features to work in the original coordinate system. So using this kind of transformational optics, you transfer the desired configuration, you can say, onto the material properties, okay, and then you put that new material into the previous coordinate system. We will take examples, it will become more clear in the subsequent slides. So since geometrical transformations generally involve changes of directions and introduce direction dependent scaling, the transform parameters are generally both anisotropic and spatially varying, okay. So this is how you will get the transform parameters. So let us consider epsilon ij as a tensor, this is the permittivity tensor, and mu ij as a permeability tensor of the original material in the original coordinate system. So, original coordinate system has the 3 axes x1, x2 and x3. Okay. Now, the elements of the permittivity and permeability tensors of the equivalent material, okay. So, that can have a superscript of E, that is the equivalent material that will bring the desired functionality, okay. And this will be in the transformed coordinate system u1, u2 and u3, okay, are then related to the original elements of this one by these equations. So, you can obtain what is the equivalent materials permittivity and permeability tensor. So, you can see here that you require a matrix A, and this matrix A is a 3 by 3 Jacobian transformation matrix. Okay. So, and what are the elements of this matrix? So, the matrix elements Aij is nothing but dou ui over dou xj, where I and j are basically 1, 2, 3. So, the matrix elements are basically partial derivatives. U is basically the transformed coordinate system and xj is basically representing the original coordinate system. So, once you know this matrix A, which is a Jacobian matrix, you can find out what is the equivalent materials permittivity, that is A transpose, then you have this epsilon A divided by the determinant of this matrix A. Similar equation is used also for permeability. Okay. Now, this we have seen the Jacobian transformation matrix, these are the elements. Now, when you have this A transpose, okay, this actually is required to calculate this equivalent material properties, and epsilon and mu, they are also 3 by 3 matrices whose elements are this one. Okay. So, you can represent the elements as epsilon ij and mu ij, fine. Now, since the Jacobian matrix A is generally dependent on x1, x2 and x3, the equivalent material that you will see will be generally inhomogeneous, even if the original material that you started with was homogeneous. Okay. Now, in a special case, when the original material is both homogeneous and isotropic, something like free space, okay, in that case you will see that epsilon and mu, these tensors are basically, or these matrices are basically diagonal, and they have equal diagonal elements mu naught and epsilon naught. Okay. So, in those case you can simplify the equation and you can write epsilon naught inverse epsilon e, that will be equal to mu naught inverse mu e equals this. Okay. This is the determinant of A inverse A transpose A. Okay. That is basically coming from those previous equations, there is nothing new here, just that here things got simplified because you have only the diagonal elements, and another important thing is here mu and epsilon are similar. Okay. So, the tensors epsilon e and mu e are then identical, okay, except for a scaling factor. Okay. So, only the scaling factors are different, other than them they are similar. Now, under these conditions, the impedance, okay. So, what happens to the impedance? The impedance depends on the ratio of the permittivity and permeability, okay, and they will remain unchanged, okay, because both of them got a factor, okay, and so the ratio will remain same, and that actually helps you, because when the ratio remains unchanged for all the polarization, you can consider this equivalent medium will have no reflection at any boundary with the free space. So, it becomes a reflection free boundary. Okay. So, let us see a number of examples now to understand the transformation principle. So, this is the first example that we will be discussing today. Let us try to create a refraction without reflection. So, usually if you have seen that refraction and reflection both come together, but you are able to make some material here which can actually give you only refraction and no reflection. So, the optical material shown here shows the ray trajectory where it only refracts. So, these are the rays, incoming angle is theta 1 and the refracted angle is theta 2. Okay. So, this is the geometrical transformation that implements the refraction without reflection kind of feature. Now, how do you begin designing this kind of a system? Okay. So, let us first start with an initial homogeneous medium, say free space, okay, where the lines will follow the straight parallel trajectories at angle theta 1, something like this. Okay. So, this we need to design the material for this one that does this kind of bending, right. So, this is our desired optical trajectory. Now, we are starting with by assuming that this part is basically free space. So, if it is free space, what will happen? There will be straight line optical trajectories, right. There will be no bending or anything. Now, it is our time to apply the geometric transformation. Now, if we apply geometric transformation in the form of stretching the coordinate system by a scale factor of s along S3 x3 direction for the part where x3 is greater than 0. So, only this positive half. So, this part is x3 less than 0, we will do nothing to it, okay, because this is the part that we want. We only want things to change here on the right side, okay, of this particular line. So, we want to stretch this portion which is where x3 is greater than 0, and when you do the stretching you actually get something like this. So, you see you just stretched the entire coordinates by a factor of s. So, all these lines they got stretched, okay. So, stretching the coordinate system by a factor of s for x3 greater than 0, okay, this one will cause the rays to change their slope, and now they will be able to follow the desired trajectory. Understood? So, we started with free space where the lines were simply going straight, then we stretched this axis so that you acquire the slope that you want to be in your desired optical response. Okay. So, the desired refraction is achieved by choosing s as a ratio of the initial and the desired slope. So, you can choose s as 10 theta 1 over 10 theta 2. This is how you can find out the stretching factor, and once you have that, you can find out the relationship between the transformation. So, this is where the transformation is coming. So, this is the transformed axis. So, as you can see in other two, so this is the plane is basically the x1. So, x1 axis is coming out of, so sorry, the plane is x1 equals 0, right. So, x1 is coming out of this screen. So, u1, the new coordinate system, u1 is same as x1, there is no change in this one, this direction. Similarly, you are not stretching along x2, so that also remains same. So, y2 equals x2, only thing has changed is u2 equals x2, and only thing that is changing is u3. So, u3 is nothing but S inverse x3. So, that is how you are stretching it. Okay. So, this type of scaling of the coordinate Cartesian coordinate system in which the direction of the axis does not change. So, what they will do? They will basically convert a cube into a cuboid, right. So, now you have known the transformation. Let us find out what is the Jacobian matrix for this. So, Jacobian matrix Aij can be calculated as dou ui over dou xj. So, that way you can fill up all these partial derivatives, and using these relationships shown here, you can calculate all this, and they boil down to a very simple equation simple matrix, that is this one. Okay. So, 1 0 0 0 1 0 0 0 S inverse. So, this is the Jacobian matrix. So, here you can see the Jacobian matrix is basically a diagonal one, where the diagonal elements are 1 1 S inverse. Okay. And you can also calculate the determinant of this matrix A, that will come out to be S inverse. Now, once you know all these parameters, you can easily find out that what will be the effective permeability of the new medium. Okay. So, you can go back to this particular equation, okay, and you can now see what happens, because these all factors are known. Okay. You can do the computation and you will see that epsilon naught inverse epsilon E equals mu naught inverse mu E equals this. So, the elements are S, S and 1 by S. Okay. Now, since the matrices that permittivity and permeability of the equivalent material, they are diagonal, okay, the anisotropic material has principal axis pointing along the axis of the coordinate systems. Okay, that is clear. And the values in this case are epsilon 1 will be S epsilon naught, epsilon 2 will also be S epsilon naught, wherever epsilon 3 will be S inverse epsilon naught. Similarly, you can find out what is the permeability along the 3 direction 1, 2 and 3. Okay. So, mu 1 will be S mu naught, mu 2 will be S mu naught, mu 3 will be S inverse mu naught. Okay. So, this is basically the requirement of the new material, which has to be replaced on this right side. Okay. So, we understood that the parameters of the equivalent material may be obtained by matching this. Okay. So, what are the requirements we are fulfilling here? The phase shift that is encountered when a plane wave crosses the stretched free space segment, with the phase shift encountered when the wave is transmitted through a unstretched segment filled with this new material, and this new material will have all this property. Okay. So, the whole idea is the phase shift that will be there for the light should be equivalent in both the cases, and then only you will be able to fill the unstretched segment with the new material, and that is how you will be able to bend the light without any reflection. Okay. So, to determine the parameters, we consider 3 waves in turn, each with the electric field along the along one of the coordinates. Okay. So, let us consider one wave, that is wave 1. Okay. So, wave 1 is a plane wave travelling along the x3 direction. Okay. So, this is x3 direction with electric and magnetic fields along x1 and x2 directions respectively. So, in that case, the appropriate permittivity and permeability are basically epsilon 1 and mu 2. And what is the relationship? So, K will be omega square root of epsilon 1 mu 2, and you can write omega. Epsilon 1 is basically S omega naught, mu 2 is S mu naught. So, you can take out S, and this thing actually gives you S k naught. Okay. So, the wave vector is basically S times the k naught in this new material. Okay. Now, this actually implies that the refractive index is basically S in n1 direction. In the original material, stretched material, the refractive index was 1. So, here it is S. So, the phase shift that will be accumulated over the distance d can then be written as S k naught into d. And you can find out what is the impedance. Impedance will be eta 1, which is equivalent to square root of mu 2 over epsilon 1. Now, this is what was mentioned before, that there will be a scaling factor. Okay. So, if you see that the scaling factor appears both places, so they will basically cancel out, and you will get the impedance to be same as the free space. So, in that case what happens? There is no reflection. So, that is for one particular wave. Now, if you consider another wave, wave 2, that is also traveling along x3 direction, but the electric and magnetic field directions are now changed. So now electric field is considered to be along x2 direction, okay, and magnetic field is along minus x1 direction. So this is x1, so you can understand which one is minus x1, okay. So in this case the wave again travels with a refractive index n2 equals s, and you can find out the impedance eta 2 will be same as eta naught. It is the same calculation as the previous one, so we are not repeating it. Then you can also think of the third wave. So this is wave 3. Now wave 3 travels along this direction, x2 direction, with the electric field along x3 and magnetic field along x1 direction. So in that case what happens, you can see that the approximate permittivity and permeability are basically epsilon 3 and mu, okay. So it should be actually mu 1 because it is along x1 direction. So consider this as mu 1, and you can then calculate what is the k. So k will be omega square root of epsilon 3 mu 1, and epsilon 3 can be written as S inverse epsilon naught, and mu 1 can be written as S mu naught. So S inverse and S, they cancel out each other, you get the same wave vector, okay. In that case the refractive index along n3 direction is also 1, okay. So we have figured out all the cases, okay. So you can calculate the phase shift along this direction, that will be simply k naught d, and this is similar in the unstretched case because there is actually no stretching along the x2 direction. So let us calculate what is the impedance here. The impedance will be eta 3 equals square root of mu 1 over epsilon 3, and that will come out to be S eta naught, okay. So you can see that there is a change in impedance in this particular direction. Now using these results you can conclude the design that the final design is basically a piecewise homogeneous. So this material is one material, this is another material, that is why they are shown in different colors, okay. And the left half of the free space is basically left half is basically free space, and right half is basically a anisotropic material, and this is also, if you see, this is basically a two axes are same and third one is different, so you say uniaxial material, okay. And this anisotropic material, as I mentioned, it is birefringent because along two direction it has got the same refractive index, but along the third direction it has got a different refractive index, okay. Now the boundary, in the boundary along the free space, okay, the interesting thing, what is the boundary along free space? That is along xn, x1 and x2, these are the boundary along the free space. So you see the impedance in those direction, eta 1 and eta 2 is same as eta naught. It means there is no impedance mismatch with the, at the boundary with the free space, so there will be no reflection, so you can only have transmission, okay. So the two factors that distinguish refraction at the boundary of this synthesized anisotropic medium from the conventional refraction at a boundary of a homogeneous and isotropic medium is that here the refraction that you are getting does not come with a reflection, okay. And second thing is that the relationship between the angle of incidence, that is theta 1, and the angle of refraction theta 2 is different here. Here it is S tan theta 2 equals tan theta 1. So this is different than Snell's law. So you can actually define your own law if you have your own material, okay. So this is how you can get your desired refraction without any reflection if you are able to realize this anisotropic uniaxial material, okay. So now let us move on to the next example, that is refraction at normal incidence. Now normally there is no refraction at the normal incidence, okay. So here we are trying to design that as well. So consider the design of an optical material that implements refraction at an angle theta at normal planar surface. So this is what is the desired optical trajectory. So this is the interface, okay, and light is falling normally, but then still you want a angle theta. So this type of refraction cannot occur at the boundary between two isotropic dielectric material, but they can occur at the boundary between one isotropic and another anisotropic material. So this possibility is there, okay. So we will start in the same process with a pilot system of free space, where the ray trajectory is along the horizontal parallel straight lines, something like this, okay, and then we will try to implement the coordinate transformation. So first thing is, so this is where the right side is basically a free space, and that is where you are able to see straight line, okay. These are parallel straight lines, but then what you want this to bend at an angle of theta. So you can actually think of this kind of transformation, that u1, the new transformed coordinate u1 will be equal to x1, but x2 there has to be some change, okay. So the new coordinate system u2 will have x2 plus s x3, okay, and u3 will remain same as x3. So you can use this kind of a transformation. So and you are only applying this transformation for the positive x3, and what is s? S is basically tan theta. So this is the angle theta at which you want this refracted rays to go. So you can use this over here. So once you know that this will be obtained when you apply this particular transformation, okay. So this transformation will deflect the trajectories as desired, and this is done by shearing along the x2 direction. So you are actually changing the coordinates along the x2 direction. So shearing the coordinate system along x2 direction for the positive half will refract the trajectories as shown here, okay. So this is what you want. So it will become like this because you are shearing it, so along x2 things will change, and that change is basically bringing this angle theta, okay. So how do you do now? So now we have to find a material that does it for us, okay. So we have to again go back to find out the permittivity and permeability tensor of the equivalent anisotropic material, and you can use the same formula, that is epsilon naught inverse epsilon e will be equal to mu naught inverse mu e should be equal to that determinant of A inverse, then A transpose, and you have A, okay. So that is the equation. Once you do it, you will get only the diagonal elements. They are 1 1, okay, no, here you get also some off diagonal elements, okay. So you get 1 0 0 0 1 s 0 s 1 plus s square. So this represents a homogeneous but anisotropic medium, okay. So once you are able to replace this new material which is in blue color, okay, with this which will have this kind of property, then you can go back to the previous coordinate system, okay, and you will get the same effect. The third example shows cylindrical focusing. So again here you have a planar interface, but this is the desired optical trajectory. So you want to achieve a cylindrical focusing functionality. So what you have parallel straight line trajectories on the left side that needs to be refracted from a planar boundary, so that they meet at a focal point, say capital F, at a distance of small f from the boundary, okay. So first what you will do, you consider this as a free space, okay. So you start, so when it is a free space, they will be all parallel straight line optical trajectory, and then you have to apply the coordinate transformation here, so that this kind of feature is obtained. So, in this case we will be using this particular feature that will focus at a point. So, again there is no changes along x1 direction. So, u1 is same as x1, and u2 and u3 will be changed as this equation. So, one will be sine function of x2 over f, another one is a cosine function. So, this will actually change the right side into a cylindrical coordinate system, okay, and this centers at u2 equals 0 and u3 equals f. Okay. So, this particular transformation converts the right side into a cylindrical coordinate system, so that you are able to get this focusing effect. So, what is happening? This particular transformation basically converts a line that is x2 equals a, okay, in the plane x1 equals 0, that is this particular screen. You can think this screen is x1 equals 0 in the original coordinate system, into a line that is u2 equals f minus u3 tan a over f in the new coordinate system. So, this is how they are getting focused, or they will meet somewhere and you will get this. Okay. And if you consider x3 equals b, that is this particular lines that you see here, because of this coordinate transformation all these lines will be now converted into circles, and I will not go into the mathematics of it, but I will just tell you that they will get converted into circles, and these are the equations of the circles. u2 square plus f minus u3 square will be equal to f minus b square. So, this tells you that the radius will be f minus b and the circle will be centered at 0 f, that is basically u2 and u3 coordinates. So, with that you are able to do this particular focusing. Now, once the coordinate transformation is fixed, now you know how to obtain your values of epsilon e and epsilon mu e. They can be done using this formula. Okay. So, you do the calculation again in the same manner, you will be able to find out what is this matrix. They are again diagonal matrix. So, epsilon naught inverse epsilon e will be equal to mu naught inverse mu e, that is s 0 0 0 s inverse 0 and 0 0 s. What is s here? S is basically f over modulus of x3 minus f. So, with that you can understand that the permittivity and permeability tensors of the equivalent medium, they have the same principal axis along x1, x2 and x3 axis. Okay. But the principal values of the permittivity and permeability tensors are dependent on the position x3. So, this is important because S is basically all dependent on this particular position. Okay. That is, the equivalent material is basically graded along the x3 direction with larger anisotropy near the focal line. So, when this goes to very close to the focal line, this value will be very large. Okay. So, this is a kind of larger anisotropy, that is what they are discussing. Okay. So, here these parameters are basically function of x3, and that is why they are all graded. Okay. So, you can understand that creating such material could be challenging, but this particular tool of transformation optics can allow you to think of this kind of materials which can do all these unusual optical transformations. With that, let us move on to the next topic, that is invisibility cloaks, which is basically an application of this transformation optics. So, an invisibility cloak is a device that can guide light around an object such that the object appears transparent and therefore it is invisible. So, here is an example. Say you have an object here, okay, but the trajectory shows that you are basically avoiding this sphere A and you are allowing the light to go through in this shell, and they will exit this at the same point where this was, so all these 4 points will be in the straight line with these 4 points. So it will look like as if there is nothing in between this. So this is how cloaking works. So anything, any object that you can put in between will not be seen. Okay. So this is the desired optical trajectory in this case. So again, how do you design this kind of a system? You can start with a free space Cartesian coordinate system which has got all parallel straight line kind of optical trajectories. Okay. And then you have to bring in the coordinate transformation. So you can convert to a coordinate system which has got u1, u2 and u3 such that the points of the sphere with radius r, okay. So you can think of radius r is having say square root of x1 square plus x2 square plus x3 square. They are basically mapped onto a sphere of radius u which is greater than a, so that this all these points are basically mapped outside. So coordinate transformation, mapping points inside the sphere to points within a spherical shell outside the sphere, will allow you to get the desired response. So what you are doing, basically all the points that is inside this sphere of radius a has to be moved onto this shell. Okay, that way there will be no light inside. Okay. So this is accomplished for all the points where r, the radius, is less than b, okay, and b is basically greater than a. So this is what you want to do. All these points has to be mapped here. Okay. So you can actually use a transformation like this: u equals a plus b minus a over b times r. So you can see what happens to the point over here. Okay. You can put r equal 0, you can put r equals a, okay, and you can find out what is happening to this transformation. So this is the transformation that allows you to do that, and when r varies to b, okay, you can see that as r varies from 0 to b, u will vary from a to b. Okay. So the entire thing from 0 to b is the entire space. So the entire space in the real coordinate system is basically now mapped onto the new coordinate system which has got u, and in that case everything falls within a to b. So what you are doing, the entire system including this thing is mapped onto this shell now. Okay. So this mapping can also be written as u equals sr times r, where sr is basically, okay, like this, a over r plus b minus a over b. So you are just bringing r in the denominator. So this becomes a position dependent scaling factor. So if you try to think of this in terms of scaling, so you can think that this is a position dependent scaling factor. Okay. So now it is your task to apply this. So when applied isotropically, the scaling factor will bring this particular coordinate transformation. So all the coordinates x1, x2 and x3 will get transformed, okay, by this coordinate, by this scaling factor. And what will be the result? The points on the straight line, say x2 equals f in the plane x equals 0, okay, of this one. So x2 equals f is, say, this one, okay, will now get mapped into the curved trajectory, okay, one of these trajectories in u2 u3 plane. So this is how all of them will now go around. So all these straight lines will now take this particular curved trajectories. Okay. So this one you can think of like this, going around. The top one you can think of like this because of this transformation. So you can also write u2 square plus u3 square equals a square u2 over u2 minus b minus a times f by b whole square. Okay. So this is the trajectory that you are seeing here. So the red curves are computed using this one, and these are the 4 values. You can also see these are 2 and 2. So, these are the 4 values. So, this is how the top 2 goes to this 2 curved red lines, the bottom 2 and the bottom 2 red curved lines. Okay. So, that is how you are able to do it, and the grid that is shown in this figure within the shell, that where U is like in between A, B, and you can actually obtain this using this particular relationship. So, there is nothing here. So, the entire space of radius 0 to B has been moved onto this shell. So, now you can put anything here, does not matter, light will never enter this, but it will go around and it will exit from this side, but these 2 points will look there as if coming straight without any deviation. So, that is how your cloaking will work. Okay. So, you can also think of similar kind of mapping for x3. So, x3 equals f is this one, okay, and you can think of putting this on this plane. So, that is how you are getting this curved grids. Now, once you know the parameters, the transformation, the parameters of the equivalent material to be placed in this shell, spherical shell, will be now determined by these equations. Okay. So, these are the equations we started with. This is the Jacobian matrix, this is the transformation, okay. This is the relationship of the transformation scaling factor, okay. This is how the transformation has finally come up from straight lines to this kind of curved lines. Once you know all these things, you can find out that you require the material equivalent permittivity and permeability to have these values, okay, where V square is basically u to the power 4 over 2AU minus A square, where U is basically ranging from 0 to A to B. So, this is how this shell has to be replaced by this kind of material that will do this trick for you. So, as you can see, this is bit mathematically intensive, but this kind of things are possibility. So, what is understood here is that the dielectric and the magnetic properties of this kind of materials in this spherical shell are both inhomogeneous and anisotropic. For example, if you take at points on the x1 axis, okay, that is u00, you will have this kind of a value, okay. And if you at all these points, the principal axes are anyways aligned to the 3 coordinate Cartesian coordinates e1, x1, x2 and x3, and you can think of the principal value u1 that varies from 0 to epsilon b minus a over b. So, this is the range over which epsilon 1 will vary, because u is varying from a to b. Similarly, the values of however, you can see here there is no variation. So, epsilon 2 and epsilon 3 will be simply b over b minus a times epsilon naught. So, the values along 2 and 3 direction will be same, but along epsilon 1 it will change. So, similar result will apply for mu as well, and with that you can see that if you go to the implementation at optical wavelengths, the implementation of invisibility cloaks via metamaterials will require the use of advanced nanofabrication technology, something like electron beam or focused ion beam lithography. We will look into the details of these different techniques in the subsequent lectures. But you can also see, because there is change graded one in the graded values. So, you have to think of constituent dielectric and magnetic elements to be of various shapes and dimensions, and they must be intricately designed and precisely laid out. So, that makes this thing very challenging. So, such elements will be highly resonant, and the electromagnetic properties of the material will depend strongly on the wavelength. So, such devices will typically work over a very narrow spectral bandwidth, and I hope you are able to understand the challenge here, that you require metamaterial to realize this kind of special functionalities like anisotropy in the permittivity and permeability, and after that also it will work only over a very narrow bandwidth. So, with that we come to an end to this lecture. So, we will be discussing carpet cloaking and other transformation optics metamaterial devices in the next lecture. So, if you have any query, you can drop an email to me mentioning MOOC in the subject line. Thank you.